Oh, as I can see, well, the end of the year and the amount of students on this lecture and the seminar are really correlated. Okay. Yeah, I hope that if you come here, then it's interesting. And if you don't come, it doesn't matter. Okay, so what are we going to do today? So today we had a lot of new definitions. So I want to discuss all these notions, and I want to, well, explore several examples. So how to compute different things that were mentioned during the lecture. So, okay. So first of all, should I recall the definition of a ring, just in case? I just want to know. Okay, who thinks that he can write the definition of a ring like immediately without any problem? Who thinks? Okay, Kirill doesn't believe that he can do this. Okay, so since no one believes in himself, let me try recalling the definition. So I mean, in general, well, when someone asks you, what is a ring? You need to give the definition in the form I gave you during the lecture. So you want to explain that a ring is a set of data, and this data satisfies some properties. So what kind of data do we have? So we have a set and two operations, plus, which are denoted by plus and dot, where plus is an operation on the set R, and dot is also an operation on the set R. And we have all these fancy axioms. What are the axioms? The first block of axioms says that the addition is good. Well, I told you that R plus must be an abelian group, but what does it mean explicitly? Explicitly, it means that the addition is associative. Then there must be a neutral element, which is denoted by 0 with respect to addition. Then each element must be invertible with respect to addition, which means that for every element, there must exist element minus a, such that a plus minus a equals minus a plus a equals 0, and the addition must be commutative. So plus a. So that was the pack of axioms where I told you that the R with addition must be an abelian group. And then I told you that the addition and multiplication must be related. Because now, if I just choose these axioms tell absolutely nothing about the multiplication. And even if I pose some restrictions on multiplication, well, there is no relation between, if there is no relation between plus and multiplication, well, it doesn't make a lot of sense, because you may choose two arbitrary operations, and it simply means that you provide two different structures on the same set. So if you have a good algebraic structure, you always want to pose some relational condition for different components of your structure. So here, since we have two different operations, we want to pose an axiom saying how this relate to each other. And the relation for the multiplication and addition is that you can open the braces, parentheses. This is how you pronounce this in English. Yeah. Yeah, by the way, you see there was a long vacation. And if you came here and you see that your ears are bleeding, and eyes are also bleeding, that's perfectly fine. That's because of my accent and my handwritings. So this is because the algebra has already started. So welcome to the hell. So this property says what is the relation between addition and multiplication. So this is property that I would like to underline by a different color. And the other two properties are the properties of multiplication. So multiplication must be associative, and there must be a neutral element with respect to multiplication. So these are properties of multiplication. So if you want to have some overview for the definition of a ring, then the axioms consist of 3 blocks. The block number 1 is about addition. The block number 3 is about multiplication. And the block number 2, which consists of 1 axiom, is the way of saying how addition and multiplication are related to each other. It's relation between addition and multiplication. So this is the definition of a ring. Okay. Are there any questions related to this definition? So yeah, that was one axiom during the lecture. I just wanted to underline how to expand the definition explicitly into the set of axioms. By the way, well, when you deal with rings, then all the properties of rings, how do you deal with rings? You just compute something with the elements of the ring. And in general, well, you just have some symbols denoting elements, and you have like plus and dot denoting these operations. And you want to compute something in general. And when you compute something in a ring, you just use properties. Well, properties like this. If you have 1 times something, you just erase 1 and you get this something. If you have something like a minus a, you will get 0. And so on. These are all very, very simple and basic properties. But all of these properties follow from the axioms. And there are some simple properties that are already the axioms, and there are some immediate corollaries of the axioms. So they are not listed here, but it's worth mentioning these properties because, well, it's very convenient to see and to use them. So first of all, one of the properties I used during the lecture is that if you have a 0 element in a ring, and if you have an arbitrary element in a ring, then the product 0 times x equals x times 0 and equals 0. So this is not an axiom, but you can prove this, that if you multiply anything by 0, you will always get 0. Well, this is what we used to with the numbers, with matrices, and all other kind of things where we have multiplication and addition. But this is a general thing which follows from the axioms. So don't hesitate to use this property. Okay, so also there are other properties that you, by the way, who remembers how this is proven? Who can prove this?
I guess we need to say that 0 is equal to 0 plus 0, and then to expand the brackets and.
Okay, yeah. Is there anyone who needs who wants me to recall how it's done? Okay, so now there is.
Yes, I want to recall.
Okay. You see, first of all, we use this property. 0 plus 0 equals 0. This is because 0 is a neutral element with respect to addition. So if you add 0 to anything, you will not change this anything. Now you can multiply this equality by x, let's say on the right. Since these elements were the same, then the result of this multiplication will be exactly the same. But now you use this distributive law, and you will get this equality. And now you can cancel out one of the summands, and you will, well, what does it mean? You cancel out. The element 0 times x, it has inverse element minus 0 times x. And you can add this element on the right and on the left. Let me be more precise. So you add this element on the right and you add this element on the left. And by the axioms for the inverse element, this thing is equal to 0. And by the axioms for inverse element, this thing is equal to 0. So you'll have 0 is equal to 0 times x plus 0. And again, since 0 doesn't change anything with respect to addition, you will get 0 equals 0 times x. Is it enough? Igor?
Yes, that's enough.
Okay, so there are other interesting properties. Let me show you. Well, if you have an element 1 in your ring, then there is an element minus 1, which is the inverse element to 1 with respect to addition. And you can multiply minus 1 by any element x. What I'm saying, there is, well, this is exactly the same as multiply x by the element minus 1 on the right, and the result will be minus x. Let's check these properties. So if you multiply by minus 1, it's exactly the same as taking the inverse of the element x with respect to addition. Do you know how to prove this? Well, when you use these properties, you just use them. I mean, it doesn't matter how to prove them, but it's worth mentioning. Yeah, okay. Yeah.
We can say that minus 1 is equal to minus 1 plus 0 and do this trick again.
Minus 1 is equal to minus 1 plus 0, and
Yep.
what?
And then if we can open the brackets, it will be like...
And you will get 0 times x equals 0. No, you're not so far from the right approach. So you need to use the definition of the element minus 1. So what is the definition? The definition says that if you add 1 and minus 1, you will get 0. Let's multiply these by x on the right. Okay? And now you can expand brackets here. Not brackets, I'm using the wrong term every time, parentheses. And now, by the definition, so first of all, we have already proven that this is 0, because 0 times x is 0. And by definition of the identity element, this is x. So we have x plus minus 1x equals 0. And now, as you can see, the element x satisfies the property of the inverse element. These elements satisfy the property of the inverse element for the x with respect to addition, and addition is commutative. Or simply, you may add minus x to the left and the right-hand side, then you will get x plus minus 1 times x equals 0 plus minus x. You just add this to the left and the right-hand side. Then these guys give you 0, and you will have minus 1x equals minus x. So this is how you play with the symbols. Who thinks that it's clear?
That's fine.
But could you show our claim again?
Well, the claim was if you multiply any element of the ring R by minus 1 on the left, you will get minus x. Or if you multiply this on the right, you will also get minus x. So we proved the first claim. Okay, so, well, if you're unsure that some property holds, you may use similar tricks to check if it's true or not. But, well, in practice, if you use some tricks to play with matrices or numbers, all these tricks work in an arbitrary ring. I mean, if a trick is general, something like multiplying -1 by x will always give you -x. Okay, so I think it's enough for like abstract nonsense. Let's try to compute something more specific. Let's
Actually,
yeah.
can I ask like another abstract question, kind of unrelated? Why are rings called rings? Like, where did
Well, that's one of the most interesting questions in the world. The first question you should ask, why group is called a group. I know this story that, well, I know that the author of the term group is Évariste Galois. He invented this term when he invented the groups. Before, nobody invented algebraic structures before him. Well, and he used this term to denote a group of permutations of roots for equations. I don't know the reason why he chose this term. Well, probably, well, you can read this somewhere. Really, I don't know. It's really something strange how the names of objects work. It's really strange. Okay, so now let's consider the ring Z12. So this is a ring with addition and multiplication modulo 12. So this is a commutative ring. So let's try to compute all possible types of elements here. What kind of elements do we know here? First of all, invertible. This means invertible with respect to multiplication. So the elements with this property. So the elements x. Then we have zero divisors. What are the zero divisors? So an element x is a zero divisor if we can find a non-zero y such that x times y equals 0. Well, in this case, it doesn't matter which order do I choose because the ring is commutative. So it's left and right. If it's a zero divisor, then it's at the same time left and right zero divisor. Then there is a third option, an nilpotent element. What does it mean? An nilpotent element is an
x to the power n equals 0.
Yep. So for some natural n, we have this equality. And the fourth property is an idempotent. What does it mean? It means that x squared equals x. So let's try to compute all these elements in Z12. Okay, let's list all the elements of Z12. 0, 1, 2, 3, 4, 5, 6, 7. Whoa. That's something interesting. 7, 8, 9, 11. Okay, this is the list of all the elements here. So let's check what is inside Z12 star. So the set of all invertible.
Why we don't have 10?
What again?
Why we don't have 10?
Oh, because I am not accurate. That's the reason. And it's really cool that you are. So what are the invertible elements here? Well, the invertible elements here are the elements co-prime with 12 actually. So let me tell you the answer. Well, the element here is invertible if and only if x is co-prime with 12. So if we want to find all the invertible elements, so first of all, let me explain why. Well, well, let's go right to left. If x and 12 are co-prime, then GCD can be presented as a linear combination of x and 12, where a and b are integer. And when you take this modular 12, this becomes 0. And as you can see, a times x equals 1 modular 12. So by definition, a is the inverse element for the element x. So if x and 12 are coprime, then x is invertible. But in the opposite direction, well, if x is not coprime, so if there is a prime number dividing x and prime number dividing 12, p is prime, then let's denote m to be 12 over p. Well, since 12 is not prime, m is not equal to 1, so it's a non-trivial remainder. Then if you multiply x by m, you see m is not as, so first of all, m is not a 0 element in Z12. And if you multiply m and x, the result is divisible by 12. Why? Because m is divisible by everything except of p, and the remaining p is inside of x. So this will be 0 modular 12. So x becomes a 0 divisor. And as I mentioned, a 0 divisor is never invertible, because if it were invertible, we could cancel by x and m would become 0. But it's not true, m is not 0. So in the opposite direction, well, if x and 12 are not coprime, then x is a 0 divisor, so it's not invertible. So this is how you prove this. Are there any questions regarding this claim?
Why is the fact that it's a 0 divisor mean that it's not invertible?
Okay, let me repeat the argument. So if you have x from a ring R and y from a ring R, and y is not 0, and you have x times y is equal to 0, then suppose that there exists x inverse. Then you can multiply this equality by x inverse on the left. So you will get this. And because we know that multiplying 0 by anything will be 0, okay? But now you can use these parentheses, and this gives you 1. So the result is 1 times y equals 1, and this is just y. And here is the contradiction.
Okay, makes sense.
Okay, so a 0 divisor is never invertible. So is it clear now?
Yes, it's clear.
Okay, so and this proof holds for any integer n, not necessarily 12. So if you take any n here, it works. So if you want to find all invertible elements, it's simple. So this is simply the way to find all the elements that are coprime with 12. So what are they? First of all, 1, then 5, then 7, and then 11. Well, all other are not coprime. So let's compute all 0 divisors of 12, of Z12. So we know that a 0 divisor is not invertible. So all 0 divisors are among other elements. So let's discuss how to find 0 divisors in a ring like this. Well, you see, well, let's say you have an arbitrary an element A from here. Well, what does it mean that this element is a 0 divisor? It means that you can take an element y from here, which is not 0, and after multiplication, it becomes 0. But what does it mean that a times y is 0 in Z12? It means that 12 divides a times y. But what does it mean that y is not 0 in Z12? it means that 12 doesn't divide y. So this simply means that, well, how do you find all those a with this property? You see, 12 is 2 by 2 by 3. So you want to take an element a, and well, I'm saying that well, a is a zero divisor if and only if a and okay, let's formulate the claim, and then it will be easier to follow what I'm trying to explain. So I'm saying that a in Z12 is a zero divisor if and only if a and 12 are not coprime. Well, actually, so as you can see, every element in Z12, or actually in Zn, is either invertible or a zero divisor. And this is how to check this. So, okay, so you see, well, we already know the claim from right to left. So we have checked if a and 12. Well, we actually have proved this. We have proven this, that if a and 12 are not coprime, then a is a zero divisor. It was above. But when you want to prove in this direction, you may suppose that a and 12 are coprime, and then it becomes invertible, so it cannot be a zero divisor. So it's also already known. So this is just this immediately follows from what we already know. So this is just another way of saying what we have done earlier. So so that's why when we found all the invertible elements, the zero divisors are all the remaining elements here, the ones that are not coprime with the modulus. Are there any questions?
Could you repeat why again?
Oh, okay. You see, so what I'm trying. So okay. So let me show you this. So if so, we want to show that X is not invertible, or X is a zero divisor if and only if X and 12 are not coprime. That's what's written here. A is a zero divisor if and only if they are not coprime. Well, let's do it again. So if they're not coprime, this part, then there is a common prime divisor. Okay, and in this case, you just take M to be 12 over P, then this is not a zero element in Z12 because it's not divisible by 12. But if you multiply A by M, you will get something divisible by 12. So A times M is equal to 0 in Z12. So if they're not coprime, A is a zero divisor. But if you want to prove this in an opposite direction, you may suppose that A and 12 are coprime and show that A cannot be zero divisor. But in this case, we have already done that A is invertible. And hence, A is not a zero divisor.
Okay, one question. Why does 12 divide, why does 12 divide A by M?
Oh, because you see, M, well, if you multiply M by P, it will be divisible by 12, okay? By the definition, M was chosen to be 12 over P. So if you multiply M by P, you will get 12. It's divisible by 12. But P divides A. So A
yeah,
is
okay.
P times something. Okay.
Okay, thank you.
So as you can see, for the ring Zn, if you have a ring Zn, all the elements are divided into parts. Invertible elements, Zn star, and the zero divisors of Zn. This is a general thing. and here you have the identity element, and here you have the 0 element. This is what happens in the end, in general. And how do you check if an element is invertible or not? An element is here if and only if x and n are coprime. And an element is here if and only if x and n are not coprime. So that's why if you have found all the invertible elements, all the remaining ones are the 0 divisors. So you don't have to find explicitly, well, this element y for all these guys. But just in case, if you multiply 2 by 6, you will get 0. If you multiply 3 by 4, you will get 0. If you multiply 4 by 3, you will get 0. If you multiply 6 by 2, you will get 0. If you multiply 8 by 3, you will get 0. 9 by 2, by 4, you will get 0. And 10 by 6, you will get 0. Well, so these are all 0 divisors. Okay, so are there any questions? Okay, so now how do we find all the nilpotent elements? Well, first of all, we know that nilpotent elements are always 0 divisors. So we just need to go through all the red elements and check if this element, well, how to say, well, if this element becomes 0 or not after raising to a power. Well, the problem here that we don't know which power to use. But what happens here in general is this. Let's discuss how to find all the 0 divisor, or all the nilpotents of Zn. Let's do it explicitly. Let's take an element A from Zn. Well, let's raise it to a power of k, and suppose that it's 0 in Zn. What does it mean? It means that n divides A to the power of k. Well, now, suppose your integer n is a product of distinct primes, p1 to the k1, etc., pr to the kr. So p1, pr are distinct prime integers, and k1, kr are just some positive integers. So what does it mean that n divides a power of an element A? How do you think? Well, if n is represented like here, what does it mean that we have this for some k?
I think that
For each p, k is more or equal than k with index on the left side.
Okay,
I mean,
so
that means just there are enough primes in A.
yeah, there is enough primes in A, which simply means that each pi divides A. So p1 divides A, etc., pr divides A, which means p1 times pr divides A. So this is the criterion. So, well, let me summarize what's going on here. So, well, okay. So first of all, if this happens, if p1 pr divides A, then when you raise A to the maximum of all these powers, this becomes 0 in the end. And if at least one pi doesn't divide A, it doesn't matter how high you take this integer k to be, well, you will never get this prime factor inside of this power. Like if there is no p1 in A, it will never appear in any power of A. So it will never be divisible by n. So indeed, A is nilpotent in Zn if and only if it's divisible by all the prime integers of n. So let me summarize this. An element A in Zn is nilpotent, and let's say, and n is represented like here, if and only if P1 and PR divides A. So in our case, n is equal to 12, which is 2 squared times 3. So in this case, A is nilpotent if and only if 2 times 3 divides A. So as you can see, 0 and 6 are the only nilpotent elements of Z12. So let me denote this on the picture. So the nilpotent elements are these. This guy and this guy are nilpotent. And all the other elements are not nilpotent. Are there any questions regarding this? Okay, and so now I want to find all the idempotents. Well, but this is simple. You just need to raise each element to a power of 2 and compare with the initial element. You can do this like simply compute, well, by the brute force. Well, there are some tricky methods explaining how to find all the possible nilpotents without this explicit computation. We can even say how many idempotents in a ring Zn, but before doing that, well, you can try the brute force. And let me tell you which elements are idempotents. First of all, the 0 element, the 1 element. These are always idempotents. And also you have 4 and 9. You may check, if you multiply 4 by 4, it will be 16, and 16 is 4 modulo 12. If you multiply 9 by 9, it's 81, and it's also 9 modulo 12, because, well, if you multiply 6 by 12 and subtract from 81, you will get 9.
Actually,
so
it's minus 3 squared.
What again?
I mean, 9 is minus 3 is the same as minus 3, and if we want to calculate 9 squared, it's the same as minus 3 squared.
Oh, okay. Okay, good. Yeah, it's even better. So this is the list of all idempotents. So the other ones are no. I don't know, should I tell you how to, well, let me tell you the answer without probably the whole proof, how to find all the idempotents and how do they look like. So, well, if you have an integer n of this form, where P1 and PR are different prime integers, distinct, well, then we have this isomorphism from the Chinese remainder theorem. Okay, so, and well, how does it work? Well, if you go from the left to right, you just reduce each element modulo the corresponding modulus. Well, it's hard to go the other way around, but you know, for example, that there is an element going to something like this: 1, 1, 0, etc., 0. So you can take a sequence here consisting of 1s and 0s. Then it's clear, then you multiply this sequence by itself, you consider y squared, the result will be y, because the operation on the right is a coordinate-wise multiplication. So this is an isomorphism of rings. So the left ring is exactly the same as the right ring. So now, since the element on the right-hand side is idempotent, then after applying the inverse map, it becomes an idempotent. So the answer is that all the idempotents of this ring appears as the images of the elements of this form here. So how many? So you take. So so if you want to find them explicitly, so you need to find this isomorphism. You need to find the formula for its inverse. Then you take all sequences consisting of 0 and 1s, and how many of them? 2 to the r, where r is the number of factors. And then all these elements, the images of all these sequences, are all the idempotents of this ring. So this gives you all the idempotents of this thing. So this is how you compute all the idempotents for this ring. So if you have r distinct primes, then there are 2 to the r distinct idempotents. So for example, there are. I didn't prove anything, just to be clear. I didn't prove this claim. I'm just saying that this is the way how you produce the result. And what is useful here is the way how to know how many idempotents you have. You see, if you have r distinct primes, you have 2 to the r distinct idempotents. So if r is 2, as was in our case, where 12 has 2 and 3 as 2 distinct primes in its factorization, then we have 2 to the 2, which is 4 distinct idempotents. And I have shown you exactly 4 distinct idempotents: 0, 1, 4, and 9, if I remember correctly. So this is the answer. This is how we do this. Now, well, is it clear? Well, is the claim clear? I mean, I'm not saying is it clear how to prove this, but is it clear what I'm stating here, how to get all the idempotents using this rule? Who thinks that it's clear what's written here? Okay, should I? Okay, then another question.
Could you repeat the algorithm again?
Okay, so the algorithm is this. Well, it's how to say, theoretical algorithm. So take this ring. It's isomorphic by the Chinese remainder theorem for the rings. It's isomorphic to this thing. So then, I mean, if you find all idempotents of the right-hand side, then you, if you apply the inverse isomorphism, you will get all the idempotents on the left-hand side. Because if you have an idempotent and apply an isomorphism, it remains an idempotent, and vice versa. So, and now here is the way to find all the idempotents on the right-hand side. You take all the sequences consisting of 1s and 0s, for example, 1, 0, 1, 0, 1, or all 0s, or all 1s, or like something 0, 0, 1, 0, 0, or something like that, or all 1s, etc. And apply the inverse isomorphism to each sequence of this form. And you will get an idempotent on the left-hand side, and this will give you all possible idempotents.
We have, for example, 2 in our sequences, not y, and we just skip it, right? So we're aiming on, I mean, if we have not only 0s and 1s in our sequence, we
then
just skip
it's not an
this
idempotent.
Okay.
It won't give you an idempotent. Well, it should be proven. I mean, it's not obvious. You need to prove this, but I just don't want to prove this. Let me demonstrate this in this example. So 12 is a product of 4 and 3, so this must be isomorphic to Z3 times Z4, where element A goes here to A modular 3 and A modular 4. Now, how do we get an isomorphism in the opposite direction? Well, as you remember, we actually need to find elements going to these two specific ones, elements S and T. And then, so what is S? S is an element which gives you 1 modular 3 and 0 modular 4. As you can see, you may take 4 here, then modular 3 it's 1 and modular 4 is 0. And what would you do in case of 1? Well, let's take 9. Because modular 3 is 0 and modular 4 it's 1. And as you can see, then element 0, 0 corresponds to 0 and sequence 1, 1 corresponds to 1. So, I didn't write a formula for the homomorphism in the opposite direction, but as you can see, we have listed all the sequences consistent of 0 and 1 on the right, and the corresponding elements on the left. So these are all idempotents. So is it clear what has happened here? Who thinks that it's clear what was here? Are there any questions probably regarding this? Okay, so just in case, let's switch to a different problem. I believe that that's enough for this exploration. We have more interesting stuff to do, I believe.
Oh, actually, I have a question about.
Okay.
Like somewhere when you were talking, you mentioned how to find nilpotent elements.
Nilpotent elements.
Yeah.
It was here. So A is a nilpotent in Zn if and only if A is divisible by each prime factor of n. This is for nilpotent. And the later one was for idempotent.
Yes, yeah, I understood about idempotent, but I missed the nilpotent one.
Oh, okay. You see, let me show you. So, first of all, if suppose that n is represented in this form, and A is divisible by each prime factor of n. Then if you raise A to the power of maximum of all k1, kn2, etc., kr, then A is divisible by n. Well, this power of A becomes divisible by n. So A to this power becomes 0 in Zn. So if this condition holds, then A is nilpotent. Is it clear?
Yes.
Now, the other way around. Suppose that, let's say, P1 doesn't divide A. Then, P1 as a prime factor is not presented in A. So when you start raising A to a power, P1 will never appear as a factor of a power of A. So A will never be divisible by P1 in any power. So A to the power of K will never be divisible by N. So it will never be 0 in the N. So that's why if this property doesn't hold, A is not a nilpotent. Is it okay?
Yes.
Okay, let's move on. Okay, let's do this. Let me show you some tricks. And by the way, should I do something? Okay, I have already discussed this during the lecture, so let's discuss a different problem. So suppose R is a commutative ring. And let's say X in R is nilpotent. Let's prove that then 1 plus X is invertible. Okay. How do you think we can do that? Oh, let's write x1 minus x. It will be easier to write formulas. It doesn't matter. Then both of them are invertible. But I just want to stick to this thing. So let me show you. So, well, actually here we can find the inverse element explicitly. And let me explain the intuition. I can tell you the answer, but let me tell you the intuition. So, well, the idea. So we want to compute something like this, you see? But then there is a formula saying that, well, it must be something like this. But since x to the n is 0, we do not have all this part. So it seems like this expression should be the inverse element. This is not a proof. This is absolutely, well, this is a nonsense. I mean, this doesn't make any sense. But this tells you how to find, how to guess the answer. So let's try this element. So let's consider an element y, which is 1 plus x plus etc. plus x to the n minus 1. And let's multiply y by 1 minus x on both sides. I mean, it's enough to multiply from one side because the ring is commutative. When you multiply by 1, you will get exactly this expression, which is 1 plus x squared plus etc. plus x to the n minus 1. And when you multiply by minus x, you will increase all powers by 1, and you will switch the sign to the minus 1. So you will get minus x squared minus etc. minus x to the n minus 1 minus x to the n. And as you can see, you can cancel all these summands, and this is equal to 0 because n is nilpotent. And as the result, you will get just 1. So indeed, this expression gives you the inverse element. And we're done. Are there any questions regarding this problem? Okay, so let's move on. Let's try a different problem. So the second part is, suppose that x in R. So R is a commutative ring as before. X in R is nilpotent, and A in R is invertible. Let's prove that A plus, well, let's say A plus X is invertible. By the way, before doing that, well, I have already proved, well, we discussed the case of 1 minus x, but it should be clear that 1 plus x is exactly the same, because you may consider element minus x. Here, this one is 1 minus x, and minus x is also nilpotent, and we can apply the previous case. Or we can do this in a similar way. But in the formula, you need to change the sign. 1 minus x plus x squared minus x cubed, etc., etc. So, who thinks that he understands how to do the same for this case? Who can do this? Okay, at least one of you is strong enough for doing that. Oh, okay. That's quite a lot. Okay, so let's try this problem. How do you think we can approach this? Are there any ideas? Okay, let me tell you. Here is a trick you can apply. Don't do it.
We can divide it by 8 probably.
Yeah, exactly. Yep. You may take A out like this. Now you see, now you have a product of two elements. This one is invertible. And if we show that this one is invertible, then the product of invertible elements is invertible. So this is how it works. If you, well, this is what we know for any operation. If you have two invertible elements with respect to any operation, their product is invertible with respect to the same operation. So it's enough to prove invertibility of the second one. But how do you do this? In this case, you may consider element A inverse X. And if you can show that this is an nilpotent, then we can apply the previous argument. So we need to check that this one is a nilpotent. So let's try y to the n. This is exactly the same as this one. So this is this product. But since the ring is commutative, we can move all these guys on the left and all these guys on the right. And this is exactly the same as a to the minus 1 to the n, x to the n. And x to the n was 0, so indeed y is nilpotent, so 1 plus y is invertible, so a times this expression is invertible. Are there any questions? Okay, let me show you how to apply this idea to find an inverse of something. Let's say your ring is Z9 of X. So these are polynomials with elements in Z9. Let's take a polynomial 2 plus 3x squared. How do you think? Is this element invertible or not? I just want to check your intuition.
Why not?
Who thinks that this is invertible? Press 1, or if you think that it's not invertible, press 0. I just want to check. Invertible, okay. How many of you? Oh, come on, guys, you're... I thought this will be an interactive show. Okay, but yeah, it's invertible. Why? Who already sees that this is an invertible element? How to prove this? You see, 2 is an element of Z9, and 2 is co-prime with 9, so it's invertible in Z9. Okay, now element 3 is nilpotent in Z9. So because 3 square equals 0, but then the whole element 3x square is nilpotent. Well, because if you multiply a nilpotent by something, as we did it here, as we did it here, if you multiply a nilpotent element by anything, you will get a nilpotent element in a commutative ring, and this ring is commutative. So we have an invertible element plus a nilpotent element. So this one must be invertible. Let's compute its inverse explicitly. So first of all, we want to find to inverse in Z9. What is this? Can you tell me?
Nine. I don't have. No.
Okay, 5. Because 2 times 5 equals 10, which is 1 modular 9. This means that 5 is the inverse for 2. That's why you see f is equal to times 1 plus 5 times 3 times x squared. And 5 times 3 is 15, and 15 is 6 modular 9. So this is 2, 1 plus 6x squared. Okay? And we can even rewrite this as 2, and here 1 minus 6x squared. And minus 6 is what? Is 3. Let's rewrite it here like that. I just want to rewrite it like this. And now if we want to take the inverse element of f, this will be the inverse element of 2 times the inverse element of this guy. The order doesn't matter because the ring is commutative. And the inverse of 2 is 5. And the inverse of this guy is just 1 plus 3x squared plus this guy squared by this guy squared is already 0. So we have nothing, and we have no other summons. And now we have 5 plus, well, 15, and 15 was 6. And this is the answer. This is how you may apply the previous rule to compute an inverse element in this particular case. Okay, are there any questions? Should I repeat something or clarify the computation?
How do we know?
Could you repeat the rule again?
Oh, okay. So the rule was here. So if you have an invertible element and an nilpotent element, then their sum is invertible. And how do I compute the inverse element? So this is the rule how I compute the inverse element. So I represent this as this, and then the inverse for this element is the product of A inverse and inverse element of this guy. And for this guy, I use the previous case. I'm sorry. I'm using the previous case, which is this. If I have an element of the form y minus x and x is nilpotent, then its inverse is of this form where n is the smallest power where it becomes 0. So I just applied all these rules simultaneously. So let me show you. So this is your A, and this is 1 plus A inverse times x in the previous notation. And now I just represented the second factor in the form 1 minus x. And we know that this x squared is equal to 0. So now when I take inverse of this product, I take inverse of the first factor and inverse on this of the second factor. For the first factor is 2 inverse, and for the second factor, it's written here. And now how do I compute inverse? Well, for the element 2, we already know the answer. And for this guy, I use the rule 1 plus x squared plus and so on. And I don't use these elements because all of them are 0. So this is the part of the formula I just used. And my x here is just 3x squared. And this is how I apply all these rules. Is it clear now?
Yes.
But this is just a trick. It's not a general rule which works all the time and there is nothing to worry about. I mean, it doesn't mean that if you know this rule, you can compute all possible inverses in the world. It's just an interesting trick which works here. And that's it. One remark. You see, the initial polynomial is of degree 2. And its inverse is also of degree 2. This is a coincidence somehow. And the reason of this coincidence is because this element was an nilpotent of degree 2. But in general, if your polynomial f has degree 2, its inverse may have degree 3, 4, 5, or like million. So in general, it's hard to predict, in this case, the degree of the inverse polynomial. So it's impossible in general to find the inverse using generic coefficients, because you don't know a priori the degree of the inverse. So somehow this is, we were lucky that the inverse was of degree 2. Somehow this is the only way how to find that this guy is invertible. Okay, let's try another problem. What if I take 2 plus 2, let's say 1 plus 2x squared in Z9 of x? Is this invertible? Let's say G. How do you think? Well,
Probably no.
yeah, this one is not invertible. Let me tell you why. Well, in general, well, if this guy were invertible, then there would be a polynomial. By the way, is it easy to prove or not? I'm not sure. So suppose there is an inverse to this guy. You see? And this should be 1. So this simply means what? So this is the definition of being invertible. But now, if you multiply the left-hand side, you will get something like 2an x to the n plus 2 plus the tail. And this must be 1. And this is the equality of two polynomials. The left-hand side is a polynomial of degree n plus 2, and the right-hand side is a polynomial of degree 0. It's just 1. So this simply means that an must be 0. So how to get a contradiction? Well, let's consider the inverse polynomial. And then it's high, and suppose that n is highest degree. So an is not 0. So it's presented in your polynomial. So, because I mean, if it's non-zero polynomial, there must be a coefficient, a non-zero coefficient, and this is the highest non-zero coefficient with the highest possible n. And when you multiply this thing by this thing, then 2 times an must be 0. So when I'm writing this, I mean 2 times an must be 0 in Z9. But 2 is invertible. Then we may multiply this equality by 2 inverse, and we will get an is 0 in Zn. And this will be a contradiction to our assumption that an was the highest non-zero coefficient of this polynomial. So this is the way you can prove that this guy is not invertible. Who could follow the proof? Who thinks that was clear? Should I repeat something? Again, guys, should I go through the proof again or not? Oh, it's clear. Okay. So let's move on and discuss homomorphisms. So just in case, what was a homomorphism? Well, if we have a pair of rings, then a homomorphism is just a map. By the way, the word mapping is the English word, and the word map is an American word. And I'm used to using map, well, because all the papers are mostly written by American guys or under influence of the American English. So currently the word mapping is rarely used. So that's why I'm using the word map. So if, but a lot of classical mathematical textbooks use the word mapping if they were written in England, for example, or by mathematicians from England. Okay, so a homomorphism is just a map. So it's a rule which takes elements from the left back and puts them in the right back. So, and this map should satisfy 3 axioms. It must preserve the addition, it must preserve the multiplication, and it must preserve the identity element. I'm sorry. So here the identity element of R, and here the identity element of S. Well, it's worth mentioning that phi must also preserve the 0 element. So it's a corollary, but it's always true that phi of the 0 element of R equals 0 element of S. This is also true. Also, there are several other useful properties that if you take, well, phi of minus x, it will be minus phi of x. This is because we know this property for a homomorphism of abelian groups, and it preserves the inverse element. And the same true for inverse elements with respect to multiplication. So if x is invertible, so if there is x inverse, then the image of x must be invertible, and this formula holds. So these are properties that always hold for any homomorphism. Okay, so let's try to describe homomorphisms of a ring Z to any other ring. So suppose we want to describe a homomorphism from Z to R, a homomorphism of rings. So if you remember, we have already discussed all the homomorphisms from Z to G, where Z is considered as an abelian group without multiplication. And we know how they look like. We just take an arbitrary element on the right and map the identity element to this one. And then we can extend this rule to the whole Z, and it gives you a unique homomorphism. So there are a lot of homomorphisms from Z to R as an abelian group. But now we want to discuss homomorphism from Z to R as a homomorphism of rings. Well, it turns out that there is only one option. Well, you see, if you take the element 1 from Z, by the definition of a homomorphism, it must go to the element 1 inside the ring R. But now, if you take element n, it's represented as the sum of 1 n times, then phi of n must go to phi of 1 plus 1 plus 1 n times, which is, let me write it like this, it's phi of 1 plus etc. plus phi of 1, and phi of 1 must be 1, so it's this, and this is n times 1r. Well, in a similar way, you can show that for negative integers, the formula holds. So if n is negative, let's say phi of minus n, in this case, you do exactly the same, but you use minus 1, so you have this n times, here's sum of these guys. And you will get, well, after the same computation, you will get this, n times minus r. So, and we may also check that if you, so, okay, what has happened here? So if phi is a homomorphism, then the image of each element of Z is uniquely determined. So element n must go to n times 1r. So as you can see, the only option for a homomorphism of rings is this: n must go to n times 1r. So this is the only homomorphism of rings. There is no other options. So let's discuss. So as you can see, there are a lot of different homomorphisms from Z to any abelian group as an abelian group, but there is only one homomorphism of rings from Z to any other ring. Okay, so let's discuss another ring. We may discuss Z of X, the polynomial ring with integer coefficients. Let's try to find all homomorphisms from this ring to R, let's say F. Let's take an arbitrary element. An arbitrary element here is of this form. So suppose we have this homomorphism phi. Let's try to understand how it works. Let's apply phi to this element. So by the definition of a homomorphism, we must have phi of A0 plus phi of A1, phi of X plus etc. plus phi of AK, phi of X to the K. Okay? Now, well, let's see what happens with all the coefficients. You see A0, A1, AK, they are integers. So actually, what we have here, so we have a homomorphism from Z to R, which takes each element A to phi of A. So we may apply the same rule, but to integers elements only. And this is a homomorphism of from the ring of integers to the ring R. But by the rules before, we know that there is only one such a homomorphism which takes A to A times 1 from the ring R. So each underlined element here is actually A0 times 1R. This one is A1 times 1R, etc. This one is AK times 1R. So as you can see, so the image of this guy is of this form: A0 plus A1 phi of X plus etc. plus AK phi of X to the K times 1R. So the only choice that we have is to choose the element phi of X. So, okay, that was some computation. So let me summarize what happens here. So let's prove. So let's try to formulate a claim and prove the claim after this computation. What I'm saying, all homomorphisms from this ring to this one are in one-to-one correspondence with the elements of R. And what is the correspondence? So if I have a homomorphism phi, it corresponds to element H, which is f of X. So I just apply my homomorphism to the variable X, and I'll get an element of R. And if I have an arbitrary element H of the ring R, it corresponds to a homomorphism phi H, which takes each polynomial to f of H. I just substitute H instead of X. So this is a bijection between the set of all homomorphisms from Z of X to R and the elements of R. So let me explain both arrows below. So first of all, let me discuss this arrow below. So if I have, just in case, so if I have an element here and I have a polynomial of this form, what does it mean that I substitute H instead of X? Well, I just do this. I just replace x with h, and I multiply everything by 1 of r. So I just do this. And all these elements belong to R. Since A0, A1, AK are integers, H and all powers of H are elements of R, so this is an expression from R. And as you can see, I can simply denote the right-hand side by the expression f of h. This is just for simplicity, but that's just the definition of this expression. I just substitute x by an arbitrary element h. And we can check that this rule defines a homomorphism. So it preserves the sum and multiplication of the polynomials. So if you have a different polynomials, which is g b0 plus b1x plus etc. plus bm x to the m, then you may take a sum of polynomials and then substitute h. This will be the same as substitute h in each polynomial and then find the sum. And exactly the same thing happens if you do it with multiplication. And as you can see, if you take the polynomial which is 1 and you apply this rule, since it doesn't depend on x, it also goes to 1 via this rule. So you can check. This is just a straightforward computation. Straightforward computation. So you can use the formula to add polynomials and then substitute h, or you may substitute h instead of each x and then use the formula. And as you can see, well, the difference between left and the right hand side is just changing. It's the time when you change the letter x by the letter h. But so that's why these formulas hold. So this is how this homomorphism works. So each element of the ring R defines a homomorphism. How does it define? Well, it says where you need to get your element x, your variable. And well, the computation above, which is here, shows you that if you know the image of a variable, then the image of each polynomial is uniquely defined by this formula. And this formula is exactly the substitution of phi of x instead of the variable x. So as a result, all the homomorphisms from here to here are just substitutions of an element of R instead of a variable x. Is it clear what is going on here?
I have one question. Why phi of a is a by 1?
What again?
Could you scroll up, please?
Scroll up.
Yeah, and here you say
here.
that phi of a is a by 1. Why is it so?
Because here we described all the homomorphisms from Z to R. They are all of this form. There is no other homomorphism of rings. And here, if I restrict phi to the integers only, I'll get a homomorphism from Z to R. So that's why it must be of this form.
Okay.
So let me summarize what's happened here. So if you want to produce a homomorphism from Zx to any ring, let's say a matrix ring. So the only thing you need to do is to fix a matrix here, like any matrix, and then you need to take the element x to this matrix. So each polynomial of f of x goes to f of a. You just substitute a matrix, x square matrix in a polynomial. So that's how this rule works. Well, for example, if you have something like 2 plus 3x square, it goes to 2 times e, where e is the identity of the matrix ring, plus 3 times a square. So this is how this homomorphism works. And so the only option is where to move your variable, because the coefficients goes exactly to the same. Well, the images of the integer coefficients are uniquely determined. And let me, well, I see that I have like -5 minutes, but I just want to formulate the last claim. So there is, so what actually we did, well, if you take, let's say, a field or a ring or anything, like say, let's say A is a ring, commutative, and let's say it's a subring of B. It's a, well, let's say this is a ring, and this is a subring. For example, R inside square matrices, like lambda corresponds to lambda E. Or this is the case where real numbers are considered as a subfield in the complex numbers or something like that. And if you want to find all possible, so now I want to find all possible homomorphisms from A of X to B, but with additional assumption that phi of A equals A for any element from the ring A. So I just want to move, so I don't want to act on the coefficients. I just want to map the coefficients to exactly the same elements. Then all such homomorphisms are also described by the image of X. So if you have an arbitrary polynomial of this form, let's say, let's write it like this, then if you want to apply phi to this polynomial f, this is the same as to apply phi to each coefficient and to x, and do it in this form. And as you can see, because of this rule, we must leave the coefficients as they are. So everything is determined by the image of X. And we can choose the image of X as an arbitrary element. So in this case, each homomorphism from A of X to B is also defined in the way the polynomial f of X goes to f of B, where B is an arbitrary element from the ring B. So this describes all the homomorphisms from the left-hand side to the right-hand side such that they map the coefficients of polynomials to exactly the same elements as they were here. Well, that's just a modification of the previous claim. Okay, guys. Who thinks that it was clear what happened here? Who can follow? More or less, okay. So should I clarify something? I mean, are there any questions regarding this or anything what was during this seminar? Okay, so if there is no questions, then thanks for being here, guys. Oh, okay.
I have a question about test and exam. Will we be able to use calculators?
Yeah, you can use calculators, but you cannot use the help of your friends. You cannot use the help of a computer, and you cannot use the help of internet or any other sources except your brain and brevity.
And calculators which calculate something modulo something are all right, right?
Oh, something. Okay, yeah, that's okay. That's okay. I mean, well, the technical issue is not the focus of the course. Well, it's fine if you use something that helps you to compute the result of like integer product or something like that. Well, Python and Wolfram is not that, well, are not allowed because they're, well, they're stronger than just calculator. Like you can find a function in Python and Wolfram doing everything that we do here just in one line. So it just ruins the whole purpose of the test. So I want to test that you know the how to deal with all these objects and you know how to apply all the algorithms. So if you just use Python or Wolfram, it means that you know how to call a function from these libraries or in this language, well, to solve the problem, but it doesn't tell me that you know how to solve the problem. So that's the reason why these things are banned. Probably I will, well, I need to modify the test in order to allow usage of Python or Wolfram, but currently I'm not ready for doing that. Okay. Are there any other questions? But don't worry. Well, the technical, well, all the problems will be carefully chosen, so you won't have troubles with computation. So it won't be an issue. At least I hope I will not make a mistake and everything will be really easy to compute. At least the level, the technical level will be not higher than during the homework. And if you do the homework, you will be prepared. Yeah.
But if I do, for example, homework with calculator, that's all right, right?
Yeah, that's all right. That's all right.
And when is, well, approximately the test? And
I think at the beginning of the June,
okay,
like after the June 6th, I believe. Because I need to, well, like during the several lectures, well, starting from the next lecture, I'm going to present you Grobner basis, and I want to include them to the test. So that's somehow a gentle introduction into symbolic computation, and I want to show you how to do that. So I need a couple of lectures more in order to include them in the test. Other questions? Okay, guys, then if there is no questions, then thanks.
Yeah,
Thanks
I
a
have a
lot.
question. I have a lot of questions, actually.
But well, I have a lot of restrictions for today, so I cannot stay here more than like 3 minutes. So be, how to say, kratki. Don't remember.
Could you open the lecture?
Okay.
I have today's lecture.
Okay, let me show you the lecture.
There was an example with matrices, and we.
Give me a second. It's. Do you mean these example?
Yeah, somewhere here you gave an example with matrices and with divisors.
Oh, okay.
Zero divisors, and I wonder why.
Why
zero divisors mean that determinant is zero?
Okay. Well, it's just one of equivalent definitions of degenerate matrices. So let me tell you how to prove this. So if determinant is non-zero, then the matrix is invertible because of the formula. Okay, there is an explicit formula. So we need to consider only the matrices with the zero determinant. So if I show you that each matrix with zero determinant is a zero divisor, then we are done.
Yes.
So if the determinant of A is zero, it means that its columns are linearly dependent.
It's not zero.
Oh, no. If the determinant is zero, then the matrix is degenerate and the columns are linearly dependent.
Yeah, okay.
So now take the coefficients of this linear dependence.
Okay.
And put them in a column from up to down. And copy this column n times. You will get a matrix where the first row contains the coefficients for the first column of A. The second row contains the coefficient for the second column of A, and so on, okay?
Okay.
This will be a non-zero matrix. And if you multiply A by this matrix on the right, you will get zero by definition.
Okay. I trust
And you can do the same thing with the rows.
Okay. Another question was about theorem or claim where triangle appeared. You said that you are going to denote all ideals as a triangle using triangle. Yeah, and question was
I mean, no. So that was a notation. When I want to say that I is an ideal, then I just write this instead of saying that I is an ideal. So the triangle is just a notation. Okay.
Okay. The question about the proof.
Which one? The second one?
About both of them actually.
Okay.
Why does it work? Because we just show that in this particular proof we have shown that if we take n by that, it's an ideal.
Yep.
But where do we prove that
every ideal is of this form?
Yeah, all ideals are.
Okay, I told this orally. Well, every ideal must be a subgroup. Okay. But we already know that all subgroups are of this form.
Okay. Yeah.
So there is no other subgroups.
Okay, I agree. And could you just go through the second proof again? But
in this case, we can do it even easier. During one of the previous seminars, I showed you that these are all possible subgroups in the N, actually. There is no other subgroups. So since there is no other subgroups, so the ideals could be among these guys. But every one of them is an ideal. So this is just a proof why every subgroup is of this form.
Yeah, could you clarify the second part of the proof? When we have this, we take this smallest. Yeah.
So X is the smallest positive element.
Yeah. Okay. And we prove that there is R equals 0. Okay.
Divisible.
Yeah. Okay. I think the majority of information is clear, but I still have a question about from the seminar, from the last task. May I ask you to conduct a consultation next Wednesday?
Yeah, no problem. Well, actually, if you wish, we could speak tomorrow if you have time. And
yeah, I have
time. Just write me in Telegram, and if I have time tomorrow, we can speak tomorrow.
Okay, great.
Okay, no problem. But now I really need to go.
Okay, thank you. Thank you. Have a nice day.
Thank you. Bye.
Bye.